Let's do an example where we're working through the mechanism and drawing products for an Aldol type reaction. So we have our cyclopentanone starting material. We have sodium hydroxide and water. So we have basic solution. And this triangle here, delta, represents heat. So this tells us that heat is added. And then we will draw and label the aldol intermediate and the final product. So we are starting with a ketone. Let's do mechanism here. Now this is a symmetric ketone. So you can, our first step is forming the enolate. We could take a hydrogen from either side. There are two here and two over here. They are equivalent. But if we have a ketone in basic solution, we're doing an aldol reaction. First step is forming the enolate. So our enolate is formed by removing an alpha hydrogen. Again, any of these four are alpha hydrogens. It would produce the same intermediate. So we remove one of those and form a negative charge on a carbon atom. So we've got proton transfer as the first step. The enolate that's formed, we have our cyclopentanone and then negative charge on the carbon where we had just removed the hydrogen. So this is the enolate. Now once we form the enolate ion, this can react with another ketone molecule. So we have our nucleophilic carbon with the negative charge, and we have an electrophilic carbon and another ketone molecule where the enolate has not formed. So we just have a neutral ketone molecule, same as the starting material. So now in this step, the nucleophilic carbon with the lone pair of electrons will add to the electrophilic carbon and the carbonyl, and we break the pi bond. So this step is nucleophilic addition. So we still have our pi bond to the oxygen. Now the alpha carbon has a new bond to the carbonyl carbon in the other ketone, and that became negative. And then this is all attached still to the 5-membered ring. So we have a negatively charged oxygen. We can neutralize it using water in the solution because it's basic solution, so water will be giving a proton. So this last step is that proton transfer. To neutralize charges, we have ketone, we have an alcohol, and so this is the aldol intermediate. So first couple of steps form this aldol intermediate. Now, with heat present, the reaction continues and forms the aldol condensation product. So that final product there. We will have a carbon-to-carbon double bond, and we will no longer have the OH group, the alcohol group. So once you formed the aldol intermediate, remember that the next step is again using hydroxide base or whatever base you have present, and you're going to remove a proton from the molecule. The proton that's removed is still from an alpha carbon relative to the carbonyl, and it's the alpha carbon where the new carbon-to-carbon bond was formed. So that's this hydrogen here that's getting removed. Now we have hydrogens over here, but if we remove one of those and form a pi bond, we're not creating another, or we're not losing the OH group. So it's always the hydrogen that's bonded to the carbon where you formed the enolate. So same carbon as what's right here. We're removing that hydrogen there. So this step, hydroxide takes a hydrogen and electrons go back on to that carbon. So we have all the same structure except no longer have that hydrogen. We have a negative charge on that carbon. Now that we've formed this negative charge on the carbon, this will form the pi bond and we will lose the OH group. So this last step is the elimination of the OH minus. So now we have a new carbon-to-carbon double bond bonded to this 5-membered ring. And so this is, in the previous video, we called it the enal product. In this case, we still have a double bond, so we have the ene, but we have a ketone, so this is an enone. Now through this reaction, we are forming that new pi bond. That new pi bond is now contributing to a conjugated system with the carbonyl oxygens. Remember, we talked about conjugation. If we have alternating double and single bonds, we have conjugation in a molecule, and that is a stabilizing feature. So now if we look at the carbons that have pi bonds, they all have an unhybridized p orbital along with the oxygen. So now we have a 4-atom conjugated pi system. And this helps drive the reaction forward, forming a more stable product with that conjugation. Now note, the aldol intermediate does not have that conjugation because we only have one pi bond. So this conjugated pi system the stability favors this forward reaction or promotes the forward reaction. Okay, so we've drawn the mechanism. Now let's write our final products, the intermediate and the product in these boxes. So we formed the aldol. We have that new carbon-to-carbon bond with the alcohol group. So that's our aldol intermediate, and our final product is the enone. And that's where the carbons the alpha carbon that has the new carbon-to-carbon bond. That new carbon-to-carbon bond is now a pi bond, and we no longer have the alcohol group. And there's our enone product.